Today we will work with the Kirchhoff's current law and its verification. So for the verification process, we will at first go to the Kirchhoff's current law theory. So if we look at the definition, at first we can see written, at any instant the algebraic sum of the currents meeting at a point is zero. We can say this, or we can say this: total current leaving a junction is equal to the total currents entering that point. So if we see this point, the currents entering here are two currents, I1 and I5. So we see I1 and I5 is entering, and the rest 4 are leaving. So from that from the definition, we can write summation of I enter equals summation of I leaving. So the entering currents are I1 plus I5, and the leaving I2 plus I3 plus I4 plus I6. So the current of I1 and I5 will be the equal to the leaving current. So if we look at a mathematical expression, in this circuit we have supplied 10 volt and we have two resistors in parallel, so 6 ohm and 4 ohm. As we supplied the voltage, the total current I will be flowing in this circuit, and from going here to here, at this point the current will be divided into two parts. This one is I1 and this one is I2. So we see that the current here is entering is total current I, and the leaving currents are I1 and I2. That is, we have written here I1 plus I2. So from that we can write total current I equals I1 plus I2, and we will test that the total current flowing in this circuit, and we will measure current across this resistor and this resistor, and we will sum this and check if this summation matches with the total current flowing in this circuit. So we will first calculate the total current flowing in the circuit. I equals V by R equivalent. The voltage supplied is 10, resistance is 2.4. So the total current flowing in this circuit is 4.17. So total current 4.17, and we will see the individual currents flowing across these resistors, and we will look for 4.17 ampere. Okay, so by applying current divider rule, we can say I1 equals this current is I1. I1 equals total current into the resistor of opposite one, R2 divided by R1 plus R2, and we get 1.668 ampere currents. Okay, the similar way, total current as second current I2 across this resistor, we get 2.502 amps of current, and if we sum I1 plus I2, we get 1.668 plus 2.50 2 ampere, and we get 4.17 ampere. That we can say these two currents equal to the total current flowing in this circuit. So this is our basic of Kirchhoff's current law, and we will next go to the experiment. So today our experiment is verification of Kirchhoff's current law, or KCL, and to conduct this experiment we need 4 apparatus, a multimeter, 3 rheostats, 4 SPST switch, and a DC power supply. So here we have a DC power supply, 1 2 3 4 SPST switches and 3 rheostats here. Also we have a multimeter. Now let's get into the circuit diagram. So what we see here is we have a voltage source here. The voltage source positive part is connected to the pole of its SPST switch, and then the through of the SPST switch is connected to more 3 switches in one common node. So 3 parallel switches here we get, and all the poles is connected to one point, and then we connect the throws of SPST switch or the other side of the SPST switch to rheostat 1, other SPST switch connected to rheostat 2, and the another SPST switch is connected to one part of the rheostat 3, and then the other sides of each rheostat is connected to one common point. So we see we can mark it here as a node. Okay, so this is one common point, and the common point is connected to the negative of our voltage supply. Okay, so let's look the connection. So now here is our voltage supply, and we have seen in the circuit that the positive of our voltage supply is connected to the first SPST switch pole, and the throw of the SPST switch is connected to 3 more SPST switches in one common node. So if we remove this part, we can see that the first pole, the pole of the second SPST switch, the third SPST switch and the fourth SPST switch are connected to a common node that is shown here. Okay, so this common node is connected to the second part or the throw of SPST switch that we have seen here, that these poles are connected to the throw of SPST switch in one common node. So we have made the common node and we will connect it here. Okay, so our SPST switches first part connection is done, and then we have seen the SPST switch, the three SPST switch are connected to the first part of 3 rheostats. Okay, so these rheostats ending or the throw is connected to the rheostats first part. Okay, these SPST switches throw is connected to the first part of another rheostat, and this one is also connected to another rheostat. Okay, so we have find it here, and then we see that the other sides of the 3 rheostats are connected to a node, and then the node is connected to the negative of voltage supply. So we see this is another part and another part of 3 rheostats, and we have made a node from the 3 of these rheostats, that is here. So this is our node, this is our node, and now we will add it to the negative of the voltage supply. So we have added the node to the negative of the voltage supply, and the voltage supply is here. Okay, so our circuit is completed. We have seen the connection of the circuit diagram, and let us take values. So at first we will power on and give the voltage supply, and at first we will take it to 10 volt. So we have given a supply voltage of 10 volt, that is 9.9 or around 10, we can count it 10 volt. And now we will measure the current in the full circuit. So if we look at the circuit here, we have told that the current of the total current can be measured from the first switch. This is here, this is shown here in the circuit. So this circuit is the first one in our circuit connection. This is here, and we will measure the current across this SPST switch. So for the measurement we will rotate the knob to milliamps here, and we have put it to the DC. So now for measuring the current, we know the SPST switches must be turned off, so our switch is turned off, and we will measure the current now. So what we get here is 71.4 milliampere. I can keep the multimeter here to get a better view. So what we get is 71.7 milliampere. Okay, 71.7 milliampere. So I will write the I. So Vs is 10 volt, I is 71.8 milliampere. Okay. Now for measuring the current across each rheostat, we will turn on the SPST switch, and for example, now our total current is flowing through this as SPST switch is turned on. So if we want to measure the current across the R1 rheostat, we will turn off this switch and measure the current across this switch turned off, and the other switches remain turned on. Okay, so the other two switches are turned on, and we will measure the current through the first SPST switch, that is the first rheostat. So we will measure the current now. That is 32.4 milliamps, you can say, that is 32.4 milliampere. Okay, so we have seen that this SPST switch or the fast rheostat current flow is currently off, and if we connect the emitter across this switch, the current will flow across the multimeter and we can see the fail. So now we will turn on this rheostat and turn off the second one to measure the I2 or the current through the rheostat number 2. Okay, so this is our rheostat 2 and this is SPST switch 2. Now we will measure the current as we have turned the switch. Seven 21.76, and the third one same way we will follow. The SPST switch is turned off for the rheostat 3 and we will measure the current. So what we see here is 18.42 milliampere, 18.43 milliampere. Okay, so for the rheostat 3 we got the current 18.43 milliampere. Okay, so we have measured the values from the 3 rheostats by our multimeter, and now we got the values. So our I was 71.8 milliamps, and we got I1 32.4, I2 21.76, I3 18.43, and that gives us the total current 72.59. So we see the current was 71.8 milliamps and the voltage raised. So I think some differences in current is very expected. So we have seen 71.8 and 72.5, that is very close. Both currents are in milliamps, and I think we can check the difference between the currents. 71.8, that is 0.7 milliamps. So if we ignore that, I think we can say that the verification of KCL is hence proven. So thank you everyone for watching the video.